Okay. Okay, so this is Lab 5 Part 2. Um, Figured out the issue. I had written this up and just hadn't finished it. So those department where it was DPTA, that was really just shorthand, meaning I need to go back and fill in the proper code. And so the first part is these functions or these things using the admit rate function. The first thing is it has to actually reference that 3D table. So the first thing is I'm telling it go to 3D table and get something. Then the second thing is I have to tell it what I want it to get. And so I use brackets and then commas. So the first comma is the rows. I don't want a row. The second comma is the columns. I don't want a comma. Remember, this is a 3D table. I want the whatever you call them jutting out off of the table, that third dimension. So it's what's after the third comma. And so for the first one, for A, I want to get what's in that A dimension or in that A variable. And so what I actually want is the rows and columns for the A variable, then the rows and columns for the B variable, and so on. That's a little bit complicated. Um, at some point, you may come back and actually want to do something like that, and you'll probably want to watch the video again if you ever want to do that. Um, But for our purposes, it breaks it down with the admission rates by department, which this is important because we can see here's a department where the admission rate is actually higher for females. Here's another one where the admissions rate is higher for females. Here's one where it's very close. Males have an edge, but just by a little bit. Here's one where females have the edge. Here's one where males have the edge, and it might even be significant. Here's one where males have the edge, females have the edge, but the admissions rates are low for everybody. 0.058 for males, 0.070 for females. And you know, what do you want to guess? That's probably where the females are all applying. Um, so our next step is, we have some variation, but actually probably most of these, so some of them may be significant. Um, But the one that I see that immediately looks like it's going to be significant is one where females get admitted at a much higher rate. Um, Here's one that may be significant going the other direction, males getting admitted at a higher rate. Uh, None of that actually is really what ends up mattering in the overall. Uh, so, so now I want to test, we can test each department um, by uh, not by doing Department A, because that won't work any better than what I just did. Um, so we're going to go chi-square by department. And to get it to work, we're going to do, can't do Department A, but I should be able to do table 3D A. So I can do the same thing that I did up there and then go, I still want to do correct equals false. I'm going to run this one just to make sure it works. And I'm going to come down here. Ah, okay, look, I don't need that. I don't care what Mark Zuckerberg is doing. Okay. Um, I'm gonna come down here and type chi-square A just to see what the result was. So it gives me the results of the chi-square test. And it turns out Department A was significant. Which one was Department A? Department A was the one where, yeah, it was the one that I said was probably significant, where females had this massive advantage. And sure enough, p-value of basically 5 zeros followed by a 3, way less than a p-value of 0.05. So now we're going to do chi-square B, and it's going to be just chi-square test. And I'm going to come back up here and copy this so I don't have to write it all out. Correct equals false. Chi-square C is going to be chi-square table 3D square brackets comma comma C in parentheses comma correct equals false. Comma D. Okay, so I've got all 6 of them. I can run them. So this is going to give me by department what are the chi-square results. And so now I can do chi-square A. Let's see. I'm going to take a shortcut here. I'm going to copy this down here, and I'm going to delete all of this just as a quick way to get just that. A little bit quicker way. You can also type it out, but all I'm trying to accomplish here is to get chi-square A, B, C, D, E, and F so that I can run them and return them. And then, so I've run them. A, I already ran, and it was significant. B, no significant difference. C, p-value 0.3, because it's 0.6145. It's definitely greater than 0.05. 0.3854, definitely greater than 0.05. 0.5852, definitely greater than 0.05. 0.3171, definitely greater than 0.05. 0.5354, definitely greater than 0.05. So it turns out in the only department where there was a significant difference between men and women, men were admitted at a lower rate. Because if you remember, so I'm going to put the 2 things next to each other. Rates A and chi-square A. The only one where there's a significant difference is the one where women were admitted more often than men. So the overall shows men are admitted more often than women, but if we actually look department by department, the only case where there's a difference is the exact opposite direction. And so why does that happen? Well, because because of the not the not the admission rates, but the application rates. Actually, I will run, I think we can see it better if I just run the, if I just show you the table that has the application rates or the total. Department A, um, lots of males, uh, applied. Um, that's the one where females were admitted at a higher rate. Department, um, let's see. First of all, let's find out the rates. Which department has the lowest admission rates in total? And we can't do that there. Um, so there's a department where women apply, the most women apply. Um, Compared to men. Well, I'm not going to make you sit here and watch on a video while I go to look for it. But there's a department that causes it to flip, and it's because, and I think it's this department, and it's because the rejection rate is just so high that the slightly higher number of females, so in that department, there are 300. No, there are more males, so that's not the department. So there's a department where the rejection rate is higher than average, but females apply there more than men. And so that's the actual root cause of it. And so we have to dig a little bit deeper to get to that. But the one thing that we can show absolutely is that the overall result saying that it's discriminatory towards women conflicts with the fact that there's no department where that's the case. The only department where there's a difference is actually slanted in favor of women. And it's because of the consequences of aggregating things together. And that's Simpson's paradox, where you actually end up not just with things being different, but things being absolutely opposite if you look at them at a lower, finer level than if you throw everything in one box and hope it works. Um, Now for the assignment for Lab 8, what I want you to do is do one sample z-test on something in your data. And so what you're going to do here um, is you're going to do a sample z-test with some hypothetical population mean. Uh, and yeah, you can make it up. Um, for this kind of single statistic thing, you're probably not going to have a good theoretical explanation for it. You can just say, oh, well, I think the mean is this for the population. Is the sample mean close? So you don't need to justify how you came up with your hypothetical mean. So you're going to come up with a hypothetical mean and test some statistic against it from your data. Um, and then just give the results in a Word document. You don't need to put the code, just your results. Um, and then for the second part, um, use the UCB admissions data and run the overall chi-square test and just put it in a table, copy it into your Word document, and give the answer these questions. Now you don't have to answer every question, but give me your impression, your own words what do you think of the data? What do you think is going on? Um, and then the most important part is going to be connecting this to your own data. So what I want you to do for this one is actually write about your data. So we're not doing a lot of statistics here. Instead, what I'm asking you to do is go as if it were the end of the semester and you were writing sort of the introduction. Here's my data. Here's a brief description of the data set, just a couple of sentences, table of descriptive statistics, and you can take that from labs 3 or 4, one of those 2 labs, and I think it was lab 3, we did a table that had the mean, standard deviation minimum, and maximum, just some basic descriptive statistics. If you want to be really good about this, you could also put in the table with covariance and correlation. And then write answers to these kind of questions. Well, actually, I said include the table of correlation and covariance. So you want to do these things as though you're basically doing the final project, because this is actually going to be the biggest part of the writing for that project. So if you do this now, then you can go back and just edit it a little later. And then include a scatter plot of, with the x variable being one variable, or the x-axis being whatever variable you think is the cause, and the y-axis being the variable that you think is the effect. And you may not get that part done until you at least get a preview of, until I at least post the instructions for the next lab, because the next lab is where we're going to do those XYs. There was one earlier lab where I did that just as a demonstration. So if you can find the one where I plotted an X versus a Y, that's what you want to do. And the reason you're going to want to do that is because if your correlation seems weak, one of the things may be that it's not a linear relationship, because correlation is only for linear. So if you see in a scatter plot that the data kind of curves, maybe it starts out going up quickly and then it kind of flattens off, or maybe it starts out flat and then picks up. If it's not just almost a straight line, the less it varies from, or the more it varies from being a line, the weaker the correlation is going to be, even though there may be a good relationship going on there. So you should do a scatter plot if your correlation isn't as strong as you think it should be. So do these things. This is mostly writing and then copying in some things that you've already done. And it's towards actually putting together the whole thing that's going to be your project. Put that at the end, put the other stuff at the front. The z-test, you can use some stuff from your own data. That's probably best just for practice. But you can also do just what I did and just make some numbers up. So the very first thing I did, you can do that. All right, and that is all. Thanks. Bye.